So my name is Yongqi Shi. I'm currently working in University of Basel as a junior postdoc. And it's my honor to be here representing my colleagues to show some experiments on gigahertz microwave imaging. So because nearly all of us are working on atomic magnetometer, optic pumping magnetometer, and I was also a magnetometer guy. This type of experiment is kind of exotic compared with our traditional magnetometer measurement. So firstly, it's a measurement for gigahertz microwave magnetic field. Secondly, it's an imaging experiment. So of course we have multi-channel scenes and multi-channel photodetectors, but here we just use a camera to really image the gigahertz magnetic field. Okay, so motivation is pretty clear. So microwave devices are very core in many industrial sectors like communication industry, security industry, and medical imaging. Especially for some quantum technology application like atomic chip to trap the atoms, and also the superconducting, they all use microwave circuits to control the atoms, and also the atomic clock. And a traditional way to detect a microwave distribution is to use a miniaturized antenna to scan across the region that you are interested in. So of course it's very slow, and also it will interfere your structure that need to be detected, and it needs very precise calibration. So there are also a bunch of some other methods to measure the gigahertz magnetic field. So our group recently has developed a new approach to image the microwave field distribution, so it can overcome all of the drawbacks compared with an antenna. And this is a nice photo. I guess all of you have seen many times. Okay, this blue square here is a vapor cell. It is designed dedicated to this application. And we have an ultra thin thickness, which is 0.14 millimeter, and it is one of the side wall is 0.15 millimeter, and it's just touched on the microwave circuits. So what we want to do is to really image the near field of the microwave, and by a small channel, this green bar here, we can control the buffer gas pressure. And this is a simple schematics. So regarding the buffer gas pressure, so there are several concerns. So first of all, we want to localize the rubidium atoms movement within the cell. So we want as many as buffer gas atoms inside. But on the other hand, we cannot do this cleaner broadening too much to make our two hyperfine state atoms overlap. So this buffer gas pressure is measured and selected just to fulfill our mission. And the nitrogen is to quench. So the longitudinal spatial resolution is given by the cell thickness, and the transverse spatial resolution is given by the diffusion distance. Okay, it's not diffusion length, it's diffusion distance which we calculated within the T2 time between the two hyperfine states that we're concerned. And we can image a 6.6 millimeter region, and this is the current speed for image. Well, I want to emphasize the principle that we are using compared with magnetometer. So we really use a pulsed way. So first we use a strong optical pumping pulse to deplete the atoms on F equals to 2 state to F equals to 1 state. And then we add a fixed duration of microwave signal. And without, for this time, there's no any light. And then we send another short duration probe pulse to measure the delta OD that's induced by the microwave field. So it's similar to the free induction decay, but the real advantage here is when the microwave is interacting with the atoms, there is no light at all. So we just scan the microwave time, and we will find such a Rabi oscillation signal. This Rabi oscillation is due to the magnetic dipole transition between these dedicated 2 MF levels. So what we do is we pump and we give a fixed microwave pulse and then probe. So we pump many times and change the microwave duration. So this is a principle. And by changing the DC field, we can easily measure the different magnetic component of the microwave field. Well, let me show this nice movie about the Rabi oscillations. We can see. So the changing of this pattern is not the movement of the atoms. It's because, so we can see here the time scale here is 22.5 microsecond. It's really very short, and it's limited by the T2 time of this 2 MF levels, which is limited by the spin exchange in high temperature. So we need to really change the microwave duration within this T2 time to gain as many as Rabi oscillations as possible. And the different atoms in different pixels of camera, they will drive Rabi oscillations in different frequencies. So with this manner, we can image the distribution of the microwave. Okay, so this is a reconstructed microwave field. And also we can measure the 3 components of the microwave field and then calculate the modulus. I want to push out some discussion about the sensitivity here because we were using a camera, so at one time the detection scheme is quite different from the continuous magnetometer. So we calculate the microwave magnetic field imaging sensitivity, which is 1.45 microtesla per root hertz, which is kind of large. But if we consider the photoshot noise, it's already 0.45 microtesla per root hertz. So in this sense, the performance is not too bad. And in the future, we plan to use a fast camera and maybe to use some continuous detection. Okay, this is an ongoing project. We would like to make our microwave imaging project on a frequency tunable fashion. So the idea is straightforward. So we just put our atoms on the hyperfine Paschen-Bach regime, and this is a theoretical calculation of the energy levels and also the possible microwave transitions in the basis of Mi and J. And this is the very first setup that we have performed to use this frequency tunable microwave imaging. And the problem is due to the strong diffusion effect from the inhomogeneity of this large field. So this is a measurement of the B field. We can see within the cell region, we have several Gauss of inhomogeneity, which will let our microwave detection impossible. And also, the Rabi oscillation damped quite fast. So the idea is we go to a more homogeneous DC field. We use a Samaria-Corbett pair of permanents like this. And recently we built a very new setup to a heating oven. And we stabilized the temperature and got some very preliminary measurements about the profile of absorption, optical absorption in hyperfine Paschen-Bach regime. Yeah, so this black curve on the background is a theoretical curve which contains many broadening with a specific buffer gas in our case, and also the different line strengths. Okay, we have done some simple measurements, and we decrease the probe light intensity and interpolate it to 0 probe power to get the absolute OD and calculate the temperature. Well, this is double resonance. So the double resonance here is similar to the optically detected magnetic resonance, while what we induce is a transition between two hyperfine states. So we fix the laser frequency on one double resonance and scan the microwave field frequency, and we can get such a peak. And for the other two transitions, we have this peak and also this peak. And there are two things here. The first one is we use 3 different double resonance transitions to calibrate the same large magnetic field, and they are matching pretty well. The second thing is the broadening here is strongly due to the inhomogeneity of the B field, so which will give us a first estimation of the B field that we are working at. Okay, in the long term, we plan to integrate a new CMOS fast camera, and we plan to combine the magnetic field and also electric field image of microwave. And we are considering some new detection scheme like continuous detection. As I just discussed with Victor, maybe we can use some locking capable camera. Yeah. And there are some new interesting physics in hyperfine Paschen bug regime, which may not be that strongly limited by the spin exchange clearance, because in hyperfine Paschen bug regime, there is quite a paper to show that the relaxation time decreases with the increase of the B field. And we also have the strong potential to put this into real applications. And this is a slide of all our members in our group. Thank you.